All right, good evening, everybody. How's everybody doing? Good. I think I know almost everybody in here, but just in case, my name is Dr. Wes Ryle. I'm the astronomer here at the observatory. Normally it would be my shop here talking to you, as President FOTO, but Mike's under the weather, so we have to come before him this evening. And so it's my honor to get to introduce our speaker for this evening, which is Dr. Michael Tucker. Coming from the Center for Cosmology and Astroparticle Physics. You said CCAP. CCAP. Don't pronounce both P's. Don't pronounce those P's. That's one B. CCAP. Michael, his background, he earned a bachelor's in physics from Appalachian State in 2017. Master's in science and master's of astronomy and PhD in astronomy, both from the University of Hawaii. Got his PhD just in 2022, and so relatively fresh coming off of it. But we still give you congratulations for completing that PhD task. But has been at Ohio State, and most of his work focuses on what he's going to be talking about tonight, astronomy in the fourth dimension, where it's time, right? So talking about how the universe changes with time, and all the interesting science that we can do with those changes over time. So help me go along.
Yeah, thanks for having me. So, like Wes mentioned, I really study how things change over time. Right? What we've learned about the universe by observing things over time. And I'll just start with showing that there are a lot of different things that change over time. And so really one of the things I like the most about my field is I've worked on almost anything you can think of in terms of astronomy, because there are a lot of different things that vary in the night sky. There's supernovae, right? Exploding stars, accretion events. So whenever you dump stuff onto compact objects like a black hole or a neutron star or a white dwarf, you convert some of that gravitational energy into photons, into light. And that has all sorts of instabilities, flares, all sorts of stuff. Or even things like comets and asteroids, right, as they pass by the sun. They change with brightness, depending on how close they are to the sun and to the Earth. So all of these are things that are in what I call the time domain, things that evolve over time, and by observing them as a function of time. And actually, I think this is distinct from most things in astronomy, because most things in astronomy evolve on far beyond the human lifetime, right? The sun evolves in 10 billion years, galaxies evolve in billions of years. But I like to study things that change on human time scales, right? Days, weeks, months, so you can find something and actually watch it evolve over however long. Now, of course, these are artist traditions or lies, right? They're scientifically informed lies. But this is not what things look like through a telescope, obviously. And so, like any good observational astronomy talk, this could be, what can we learn from dots? But it turns out we can actually learn a lot by looking at dots in the sky. We've been learning a lot from dots in the sky for actually quite some time. And so here, is an actual dot in the sky that shows this is the most favorite dot of 2023. This is the supernova 2023 IXF. We named supernovae. Call them transients, really anything that's going to be a dot in the sky. We don't know what it is yet. Typically, supernovae, a bunch of some other things, but so this was, A is the first one, B so far. So IXF is more than 26. We even get to, 10,000 per year, 20,000 per year in the modern era of surveys. But even before we got computer processing and all that, we were actually learning things from dots in the sky. And so I'll kind of give you a little trip through time just to kind of lay the groundwork on how we actually learn things from dots in the sky. And then two things from just the last 5 years or so that I've worked on at least, I thought have been really interesting, and you can see I kind of crossed out what I was going to talk about because a week ago something really interesting happened. We'll get there. But of course, we'll start with the past. I thought that was, especially if they didn't consider it, this is one of the historical observatories. It turns out we've been seeing dots, new dots in the sky for quite some time. A little unclear when humanity saw the first new dot. The first one that's unambiguous is supernova 1906, and it's unambiguous because it was bright enough to be seen during the daytime for like a month, right? It's extremely bright, and it's reported all across the world. The best, reporting are from the Middle East, Asia. There's some examples from Yemen, Japan, but it's even recorded as far north as Scotland, even though it was like 10 degrees above the horizon from that latitude. And so this was like the first, unambiguous thing that was, seen changing the sky. And we've actually gone back and, since these reports not only included there's this brightening thing in the sky, but also included a buff estimate of its position, relative to the stars that are nearby. We've actually found the remnant of that supernova. It was a shot of an X-ray image. It's still, kind of mind-boggling to me that we can look at something with modern, detector technology from a spacecraft and connect it to what people reported 1,000 years ago. Of course, if you were alive in the supernova, or if you were alive in the year 1006, this was not good, right? Because this was very much still in the era of Aristotle, at least his worldview, where the heavens are perfect and immutable and unchanging. And so seeing something change in the perfect, immutable heavens was universally interpreted as bad, right? You had anchored the gods in some way, and this was signs of divine retribution was imminent. So it's really another 500 or 600 years before there was a new dot in the sky that we could actually do something useful with, or something that approaches modern science with. But it was tidal supernova in 1572. This was actually a pretty exciting time for astronomy, because there was tidal supernova in 1572. And again, right, it's the eye, right, it's Nova Stella, new star. And again, we've, actually moved. We've actually, gone back and found the remnant. This is in the infrared, so this is you're looking at the dust from the explosion. But you can, actually see that's the star, or at least the debris from the star that exploded 500 years ago or so. And there was tidal supernova in 1572. The Great Comet of 1577, I think, was the year, which was right under the scene for 2 months. So there was Kepler supernova in 1604. And so this was a really exciting, 30, 35 years for astronomy around the globe. And by this point, we had figured out parallax. It's the idea that you can see something moving, it has to be closer than something you can't see move. Right? If you take one step to the side in front of you, you move a lot more than if you were in the back of the room and took one step to the side. Same idea with the planets, right? If you can see the planets and the comets move, then they're in the solar system. And the fact that this new dot did not move, then it must be part of the celestial sphere, the heavens. And so this was evidence, some of the first evidence used by Galileo, Tycho, and so on, that there was things that could change in these so-called immutable heavens. And so we were slowly pushing away from the Earth-centered model of the universe, slowly moving towards the solar, sun-centered model. Still took some time, but this was, a big piece. But even here, we're still in what I consider the human eye limited regime, because you're still relying on some person looking through a telescope and drawing or writing down what they saw. And then not only were there transcription errors, the human eye is not a great detector. Evolution prioritized, avoiding saber-toothed tigers or spotting bears on the ground, whereas reliable and consistent measurements of positions of stars was just not big for evolution at the time. And so there's all sorts of errors, not to mention, as you try to pass down those papers, like you wrote something down, if you spilled some coffee on it or stepped on it, right? All sorts of things can happen. And so it took another 400 years or so to the first real detectors, at least in astronomy. So these were photographic plates in the 1900s, the early 1900s. And so this was great because you now could take an actual image of the sky and then be, somewhat faithful to what you actually saw through your telescope. You can make measurements and whatnot. But they had lots of drawbacks. Each one weighed, I think, several pounds. So every time you took an image, right, that's 10 pounds. You take 100 images a night, right? You're getting into metric tons very quickly. Not to mention, right, there's a supernova that is different between these images, but I would pay you $10 if you can find it in 5 minutes, right? There's one dot that is different, but it is extremely hard to see. Even with the arrows drawn on it, I can't see it unless I go to a computer and read these. And so, not to mention that these had all sorts of, defects and were really difficult to calibrate because you basically had a sheet of glass that you put, it's called an emulsion, basically a coating that's sensitive to light. So when you put it behind your telescope, the photons, the light basically burrowed into the emulsion. But if you had any impurities, which of course you did, then you could deviate to the left, you wouldn't accurately calibrate how bright it was, or all sorts of issues when it came to reliable observation of the night sky over time. Right? So this is where it really wasn't until the late 1900s or the 1990s is when new technology kind of evolved. First with CCDs, charged coupled devices. There's one up here, and it's basically the bedrock for a lot of the modern low-cost imaging, even in your phone. Right, a lot of that's been charged coupled devices. CCDs. They're cheap, relatively easy to make. And then, of course, computers. And there's the first computer, which was larger than this room. Of course, the fact that I'm giving the talk on the laptop or your phone in your hand in your pocket.
This room actually used to have old IBM computers.
Really? Yeah. So this openly works to digital image processing. So no longer you just sit and squint at every little dot on your photographic plate. You could actually do computer processing to do a lot of the things that you used to have to do by hand. So this really opened up observing the night sky over time, where you could take a picture over several nights and not have to sit there and count every star individually. Right? You can do this in an automated fashion and look for things that change. So this really only came to be in the last 25 or 30 years. And so I can go back to that image I showed you earlier, and it's actually a movie. Right? So I work with the Assassin survey a lot, and it's all sky automated survey for supernovae. And their whole thing is they're a sky survey. They want to do it as cheaply as possible. So you see there's one of the pictures of their cameras on their mounts. And it's we call them mini telescopes, but it's really just really fancy photography. Right? These are Nikon lenses on a telescope mount. You can get a whole setup. Each of these mounts, since they're so cheap, we have five mounts across 4 locations, and we're working on finishing a 6th. So the idea is have weather redundancy. We survey the whole sky, or at least the whole light sky that's not facing the sun. Pretty much every night. I think our typical return time, imaging the same piece of sky, it's about 20 hours. So you can do this, right? The hardest part of making this little mini movie was downloading the data and making it look nice and actually, turning it into a before file. All of the data reduction and calibration, all of it's automated, right? So this is all just open up the telescope, take some pictures of the sky, send it to our servers at Ohio State, does the reductions. I can just go and say, how bright is this piece of sky for the last, it's been running for about 7 or 8 years. So that's really, the status of the field in the present day, right? So I work, mostly with Assassin, but there's a lot of different surveys going on, and each kind of has their own footprint, you could say, right? It's active as cheap and tries to do the whole sky as quickly as possible. They can do that because it's really inexpensive to make one of these counts. But as you get to the bigger surveys, like ZTF, Zwicky, Transient Facility, or Pan-STARRS, I'm not even going to bother saying that. But these are, like the 1.5 meter, I think Pan-STARRS is a 1.8 meter telescope. Right? So they can go much deeper into the sky, but as you go deeper into the sky on a bigger telescope, typically your field of view shrinks. And so there's a lot of trade-offs. And so these actually work really well together between kind of your smaller surveys that cover more of the sky, but don't go as deep, versus the bigger surveys, which can do this, go deeper into the sky, but typically can't cover the same amount of sky in a single night. So this has really opened the door to a lot of really interesting things, looking for things that change, as a function of time, right? Because now these are just running every night. And I can get alerts into my email saying something changed, right? You can basically say, I want some brightness limits, I want some cadence, whatever. Everybody just says, here's something that matched your files. And so the first thing I'll kind of tell you about that's been really interesting in the last 5 years or so, supermassive black holes having a snap. So first we'll start with the star, right? So imagine a star. So gravity is always trying to pull in all the material from your star. So it keeps trying to pull in, right? It makes it collapses from a big molecular cloud and fragments so you get to what's going to end up being your star. As it collapses in, it'll keep collapsing. You ever seen the videos from the International Space Station when they have some water bubbles? Right, always get spheres. Every time, whenever gravity's at work, it wants to make a sphere because it's pulling all the way on all directions. They're most stable geometric shape when everything's a fluid sphere. And basically, the stars are just burning balls of water. Right? It's, we call them plasmas, but it's basically aqueous fluids. And so as gravity pulls in, it's a sphere. But you need something to keep it from collapsing all the way into nothing. And that's basically at a certain point, you collapse so much, as you collapse, you start to pressurize the interior. You increase the temperature, and eventually you actually ignite the core. Right? So the sun is burning hydrogen into helium, and that's what creates gas pressure to push that fight against this gravity. It's the same thing with like your tires in the winter, right? Your car tires deflate a little bit in the winter because it gets cold, right? And as it heats up, it wants to expand. Same idea, right? To keep the stars from collapsing into nothingness, you need something to push out, and that's the gas pressure from nuclear fusion in the cores of these stars. But of course, let's say you have something like the Earth, which is hanging out near the sun, right? It looks like our Earth is hanging out around our sun. And gravity doesn't care where things come from. So the Earth is pulling on the sun a little bit, just as the sun pulls on the Earth. Except that the Earth is so small that the sun doesn't really care. But you can say, well, what if you have something much bigger? Perhaps a black hole. And then the star might start to really care. I'm going to put an equation, so don't panic. But if you had some particle of gas on the outside of your star, it feels the force from the star trying to pull it in. But now you have this other thing that's also pulling on it. So you can just solve for where does the gravity of the black hole equal the gravity of the star. That's when things start to get really, really bad for the star. Turns out to be somewhere around 1,000 times the size of the star. Then that star starts to, the gravity of the black hole essentially starts to overwhelm the gravity of the star. So you start to just tidally destroy, right? Gravitational tides start to just pull the star apart. And so this is what we call a tidal destruction of gravitational tides. So as the star just passes, it wanders through the galaxy and ends up too close to a black hole, you'll just shred it apart. This is called a tidal disruption event. Roughly half the mass is flung off into space, and the other half creates an accretion disk around the black hole and usually has this orange stuff. So we found maybe 15 or 20 of those so far. These were predicted since the 90s, but it wasn't until we had surveys that could do this, because these also happen in the middle of galaxies. If you're taking a picture of a galaxy, typically the centers are really bright. And so looking for changes in the brightness of the centers of galaxies is actually pretty difficult. So it really wasn't until the modern era of automated digital image processing where you could do this systematically to actually look for these types of things. Otherwise, it was just too difficult to calibrate how bright is the center of your galaxy. Because that is actually a pretty difficult measurement. But what's even more interesting is, let's say the star is just a little bit farther out. It's not going to be completely destroyed, but if you move it just a little bit beyond that disruption radius, it'll still feel some gravitational effects from the black hole. You'll get some stuff stripped off, but you won't destroy it. So if that star is bound to the black hole, it's in orbit around the black hole, then you can have multiple of these happen. We call it a partial tidal disruption. So here's actually a pretty nifty video made by NASA. I'll explain exactly how we got to this, but I just really like this video. So it shows basically if you have this star orbiting this supermassive black hole, every time it makes this closest approach, it gets tidally distorted. A little bit of mass is stripped off, and that gives you this flare. But it's not completely destroyed. It's just outside that complete destruction zone. And so, how do we actually, get to that, something like that video? So this was discovered by my friend in grad school in Pain. she was looking for, galaxies doing weird things, and she realized this one seemed to have flares about every 115 minutes, right? This is brightness, right, on the y-axis, and then the time. You can see, right, there's these little spikes. On that. And so, you can actually measure, how often do these spikes happen? Do they happen at the exact same time? And the answer is not quite. So if you actually go and say, do these happen at the same orbit, right? The Earth's orbit is 365 going forward. And that doesn't really change, right? That stays pretty constant, which is good for us. But this actually is speeding up slightly. So if you take basically you just take where's the brightest point and say, is the time between this one and the next one always the same? The answer is no. So there's a speeding up very slightly from the flare of light. That's this trend you see. You can see we actually discovered it, and discovered it in flare 17. Because the really interesting and really useful part of these partial TVs is when they're going to happen within a few hours. So you can schedule all your big telescopes, all your space telescopes to look at it at the right time. Because the hard part for completely destroyed stars is when it's going to happen. And so you don't have any good way to schedule all your big telescopes with their fancy instruments to look at the right place at the right time. With these partial PDBs, right, you can schedule ahead of time. We run a whole bunch of telescope proposals. And so this actually shows that not only is this galaxy have a bunch of bright flares about every 3 months, those flares are speeding up, right, within a few hours between flares. So there's really only 2 ways you can get flares from the center of a galaxy that speed up with time. One is double supermassive black holes, but this is too fast. Right? If you have 2 supermassive black holes that were spiraling in, that's governed by general relativity, and that should take about 10 times longer than what we see here. But if you, instead of having 2 supermassive black holes, which are obviously millions, if not billions times the mass of the sun, you take something that's a supermassive black hole and a regular star. It's about what this is. So that's how we get to something like this, is that we saw bright flares from the center of a galaxy every 3 months, and those flares are speeding up by a few hours every time. And so this really is every time that star makes a close passage by the black hole, you strip some mass off, that gives you the flare, but then also you shrink the orbit a little bit. And that's why it speeds up. And so basically, this matches all. And so actually what we're really waiting for now is that this should fail at some point. The hard part is we don't know when this started, right? Basically, as soon as we started the survey, right? Let's go back to that. Right? But these flares have been going since we started in 2013 or so. And you just say, we know how bright it is, and we know about how efficiently a supermassive black hole can convert mass being dumped on it into photons, into lights. And this really is, a few fractions of a Jupiter mass. So even as far like the sun could do this hundreds of times, and just keep going. So we're actually waiting for this to do something different, because that would signal that it's, entering a new phase of its evolution. But we don't know if that's going to be next year or in 100 years, because this could go on for quite some time. And so these partial TDEs have been really interesting, because what it seems like, at least from the 5 years that we found these, is that it seems like we can study the structure of stars in other galaxies. Because imagine, you just have a ball of lead or a ball of metal, right? That's going to respond or not respond to a supermassive black hole, exerting gravity on it, versus a ball of water that will respond to gravity acting. And so as you change the mass of the star or the age of the star, you change the structure of that star. And that changes how it will respond to being tightly distorted by the supermassive black hole. And so since this is happening over and over, you can basically get away, you can see the star ring as it gets, because it's going to get deformed, become this oval, and then kind of ring down. And so you can basically test what is the structure of the star as it goes through all these interactions with supermassive black holes. So there's, some ways where we can study the structure of stars in our galaxy. But this is really the only way where we can even attempt to study the structure of stars in external galaxies. And so it's still a little difficult to go from, right, you see the light curve with a bunch of flares, right, going from that to something actually interesting about the structure of the star. That's what theorists are currently, arguing about, of, how do you actually convert what we observe into something scientifically useful. But the consensus seems to be that this seems to be a really promising way to actually study how stars in other galaxies respond to being tidally distorted by supermassive black holes. In addition to being a way that we can study black holes, right? Because not only does the disruption depend on the star, it also depends on the black hole. So the spin of the black hole will determine, if it's rotating, if the black hole is rotating in the same direction as the star's orbit, and that will affect how the disruption occurs versus its retrograde orbit in black holes. And so these partial QEDs look like they're going to be a really promising way to understand stars and their structure in galaxies far, far. So that's really exciting and just a really cool topic. So that's the first part. I'll stop here for any burning questions. Take a sip. All right, we'll keep going ahead. All right, now we're going to completely change topics. And first, we're going to start with, I guess I'll say, I rewrote pretty much this last third of my talk in the last 2 days because we found something like a week ago. And so, apologies if I'm a little choppy, but it is pretty interesting stuff. So first, we'll start with the solar system. This is not to scale. Right? This is the size scale, not the orbit scale. And this is just to show that the Earth is pretty small. Right? There's Jupiter is the biggest planet. You can fit about 1,000 Jupiters inside the Sun. You can fit about 1,000 Earths inside of Jupiter. And so, but if you want to actually look at the orbits, right, this is where this upper one is everything that's inside of Jupiter. And
not on the TV.
Yeah, that's fine. And so basically the entire inner solar system is in that tiny little ring on the bottom. So basically most of the solar system is just empty space. I think if you added up all the sizes of the sun, every planet, every asteroid, every comet we know of, and just said how much of the solar system is empty, it's like 99.99999%. Right? It's almost completely empty. But what's similar to the supernovae I talked about, we've actually seen some of these for quite some time. Because you'll see there's the asteroid belt, which is just inside of Jupiter. That's mostly rocks. So these are close enough to the sun that the ices that are on their surface have been sublimated, similar to evaporation. Right? Sublimation is just solid to gas, which typically happens in space because it's low density and super cold. But it's the same idea of evaporation, water evaporating into the atmosphere. So imagine a block of ice turning into gas instead of. But it's not till you get to the outer part of the solar system, when it higher up, where it's cold enough, the sun is not bright enough for all of these to have their ice sublimated away. So you have snowballs on the outside. And so this will become really important later on, this difference between the asteroid belt, which is dry, and the Kuiper belt, which is wet, snowy. We actually observed comets for a couple of thousand years as well. And so here's even from an old Chinese tomb that was dug up from the Han Dynasty 2,200 years ago. Here's 7 comets that they had recorded over the entire recorded history. There was actually like 30 in their whole tapestry. So we've been observing comets for thousands of years. And even, like I said, the Tycho Brahe's time was a really, really good time to be an astronomer. So he also got to observe the Great Comet of 1577. This was, bright enough to be seen during the day for 2 months. And so he actually, his numbers ended up being pretty wrong, but the gist of it ended up being right. because he realized two things. One, the orbit of the comet didn't seem to center on the Earth, which was a problem for the whole, Earth-centric model for the solar system. But even more so, the tail. And so the comet tail is basically as these icy things are heated by the sun, you start, melting or sublimating that ice, and so you get these long tails. And so he realized that the tail didn't point back to the Earth. The tail pointed away from the sun, which would also be, problematic for any theory where the Earth should be kind of the most important thing in the nearby universe. So both of those are actually pretty big points in arguing against that whole Earth-centric kind of idea for the solar system. But then again, right, as we've gotten into the modern era of surveys that scan the whole sky every night looking for things that changed, we started looking for all these asteroids. They mainly focused on comets back in the day because asteroids are really hard to see. If you don't have those ices on the surface, it's just a rock. And so rocks, don't emit a lot of light, and they also don't reflect a lot of light. So it really wasn't, we discovered a lot more comets than asteroids. And that's where things get really interesting. Because a week ago, or I guess it was really 2 weeks ago, but it was published a week ago, we found the third ever interstellar object. And this is basically an object that you can see here, right? Here's your survey images with a gazillion stars. You see that little dot, right, that moves. And this was separated by about an hour, right? And so with modern computing capabilities, you take a picture of the sky, you detect all the stars, you do the same thing for your next image, then you see is there anything moving, right? This is where computers become super, super useful, because trying to do this by eye would be awful. But it basically says, if there's any stars, because the other thing is, you also have this image of there's no comets, there's no asteroids. So you know that this dot is there. You also know that the dot moves from image to image. And so there's, whole computers dedicated all the time to just trying to link asteroids or link comet trajectories, because they should consistently happen from image to image. And so they flag this one, and they flag this one, because if you solve the orbit, it does not make a circle. So that's how you know these are interstellar. Right? And so we've actually found 3 of these, and the new one is this one. But you can see for any of the black lines, you can't make a circle from it coming in and going out. Right? It doesn't make a circle. So they are not bound to the sun. I'll say now it's not aliens. Right? People love to say aliens with the interstellar objects. It's not. But it is really interesting because there's really interesting ways where you can actually populate the Milky Way with just a bunch of trash from other solar systems. And so, actually, when I was starting graduate school, this was in the fall of 2017, and I was at the University of Hawaii, which was a nice signature. And it was discovered by a survey in Hawaii and stars. And that's why it has the name Oumuamua, because it was a nod to the native Hawaiians. And the Hawaiian means the first messenger or scout. And so, we've been through a lot of, press releases and talks on this, because this is the first time we've ever found anything that was not bound to our sun, right? Anything in the solar system that was not bound to our sun. And I was actually taking a class at the time. And so, I guess for anyone who's not familiar with Oumuamua, it was really interesting, not only because it was from outside the solar system, but also it's some weird shape. You can see it's, people call it a cigar or maybe a turd, but it's this long, skinny thing. And so, a common question I get is, how do you actually infer that? How do you actually get, a shape of something? And light curve, the light as a function of time. Because remember, asteroids and comets do not emit their own light, right? It is all reflected sunlight. And so, as you watch the light from these objects, you're watching basically what surface area is the reflected light coming from. So if you had just a sphere, a ball, right, you would see no change in the light because all the sides look the same, and as it rotates, nothing is changing. But as you get away from a sphere, as it rotates, as it turns, you'll see different sides, and basically different amounts, different sizes are reflected. And here's a nice little thing from NASA. But basically, as it turns, you see different amounts of reflected sun. I accidentally cut off that axis here, but the difference between the dip and not the dip is like a factor of 10 in brightness. So this is a huge change in brightness. And so if you want to just do this by geometry, so reflected light, it has to be something of like 5 or 6 to 1 in terms of axis ratio, right? So one of your axes has to be 5 or 6 times longer than the other one to get a 10 times change in brightness. So I think that's just cool. And there's also some stuff about tumbling, because you see it's not periodic. So it's not just rotating, it's also doing this the whole time. Because otherwise you'd expect, right, if it was just rotating around one axis, you would see it would always show up at the same time. But if you have another axis, then things are going to change every time, just a little. And so this is actually this, weirdly shaped tumbling spacecraft. So this is, super exciting. There's a whole bunch of papers trying to explain, where it came from, how it formed. And I was actually taking a class at the time, my first semester of grad school, called the Order of Magnitude Astrophysics. And the idea is that using a whiteboard or a chalkboard and knowledge in your head, you should be able to answer pretty much any question to within an order of magnitude, or a factor of 10. Right? How many hairs are on your head? How many people on the planet? How many interstellar objects must there be if we found them? Right? So you're going to say, pan-stars, which is the survey that found it. You're going to imagine every time it takes an image, it's shooting a pencil beam through the solar system. And if you have an object in that pencil beam, you would detect it to some distance. Right? If it got too far away, then it's too faint, so it's reflected light. So every time you shoot a pencil beam, you're sensitive to some distance. And over 3.5 years, it's taken like 10,000 pencil beams. So you can just calculate how much volume has it sampled over those 3.5 years. So if you found one object and this volume that you sampled, now you have a density, right? Now you have an object per space. And so it turns out, from 3.5 years, you also have to do some stuff for completeness, because if they're moving too fast, then your computer algorithms have difficulty tracking in between images. Remember, some images that show it's moving too fast, then it'll be difficult to say, oh, in this image, we found a dot and it matches that image over there. But if it's moving slow, you can actually do this pretty well. So, things get a little tricky, but for the most part, you can account for these things, or at least estimate them. And it turns out, we did all these estimations. And that means if we found this one thing that happened to pass close enough to the Earth for us to detect it, then there must be at least one of these within Jupiter's orbit at all times. Right, and so there's one of these inside of Jupiter's orbit at all times. If you remember back to the slide on the solar system, Jupiter's orbit's a minority of the solar system. So there must be hundreds of these in the solar system at all times. They're just too faint for us to see, right? I mean, think of the picture, right? There's a very faint little dot amongst all of the stars. And so these must be quite common. They're just so small that they're really hard to find. So if we assume that there's one within Jupiter's orbit at all times, there's hundreds in the solar system at all times. There's hundreds in the solar systems at all times. There must be trillions, millions. So you can start to ask order of magnitude questions, like if every star contributes, space garbage, how much must you produce to match the one that we found? And so there's 2 times in a star's lifetime where things are chaotic enough for you to throw a bunch of garbage out in space. The first one is when the solar system is formed. So these are actual images from Malta to Radio Array in Chile of protoplanetary disks. So these are stars that are just being formed, and around them are these disks of pebbles and rocks that will eventually form planets. Even you see these rings, right? Those are planets that have sculpted out you're sensitive to like millimeter size here. And so basically all these gaps you see are basically those Jupiters in other solar systems that are carving out the little lane in these disks around these baby stars. Right? Our sun did the same thing. We actually have evidence for our solar system going through something similar, because once you've formed most of your planets, they start throwing out whatever's left. Right? So whenever you have a big planet, if you don't quite capture something, you'll fling it out instead. And so as your big planets form, they either gobble up everything or start chucking it out. And so we actually have something called the late heavy bombardment, which happened towards the end of the sun being born. You can see here, right, here's an actual simulation where if you start with all of the big planets, as they start to move to their final locations, you're going to have all this debris, which ends up becoming what's left of the asteroid belt. But as your big planets start, muscling your way through the solar system, they start chucking stuff everywhere. And so some of it comes in. So a lot of the evidence for the late heavy bombardment is from craters. So mostly the Moon, Mercury, and Mars, because those three have little or no atmosphere. Now, you don't like to do this on Venus or Earth because atmospheres, wind, and rain erode things, and so it becomes really difficult to trace things back. But things like the Moon, right? If you see a big crater with no little craters in it, that means that was the last thing to hit that spot. So you can start doing a lot of estimates of how many little things hit over time, how many big things hit over time, and basically the Moon, Mars, and Mercury all show evidence for a huge amount of big things hitting them all around the same time, which was about 4 billion years ago, just after the sun was born. And so basically this was Jupiter and Saturn muscling their way through the solar system, chucking out anything that got in their way. Some of it went into the inner solar system and smashed into the Moon, but 20% was flung in the other direction and got thrown out into space. So this is the way you can get something that's dry, like the Moon one, weirdly shaped. It's a rock, it's a fragment of something else that got beat up. The problem was there's just not quite enough stuff. Right? Even if you go back, right, you can, people actually estimate how much rock material is in these disks, and there's just not quite enough to give you the numbers that we need based on our estimates of how common these are. So this, didn't quite work out. That was, several classes worth of order of magnitude questions of how much mass are in these things, how common is it for one to get thrown out, yada, yada. But the numbers never quite worked out. So we started looking at a second option, which is when the star runs out of fuel. So here is, the very, 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 very short version of stellar evolution. But basically, our sun is right here. It's using hydrogen and helium, which is great. So that's about 10 million years. Once it runs out of hydrogen, it's going to fuse helium on this big red giant. So it's basically becomes a big puffy thing. But then once it runs out of helium to fuse, then it has this big envelope that it kind of shrugs off. Right? It no longer has anything to support it. And so you're just left with what's left as a white hole. And so you actually lose about a third of your mass in this process. If you remember back to that scary equation I showed, gravity depends on mass of both objects. Right? So the Earth is pulling on me just as I pull on the Earth. And then if the Earth lost a third of its mass, right, you would all start jumping really high. So you can imagine if you are one of the objects in the outer solar system, like the Kuiper belt, already your tether to the solar system is pretty weak. And so if you just lost a third of the sun's mass, you can just release this stuff into the ISM, the interstellar medium. Right? You no longer have the gravity to keep it. And even beyond that, I didn't mean to mention it earlier, but there's also something called the Oort cloud. We know even less about it than the Kuiper belt. But we know it must exist because we see comets that come from way beyond the Kuiper belt. Right? They're rare, super rare, but they happen. So there has to be some stuff that is beyond even the Kuiper belt. We just have very little knowledge about it, but they're there. And so basically, when your sun loses a third of its mass, the stuff that's just already barely hanging on just gets released. And so this can easily produce trillions of things that are just floating through the Milky Way. The problem is, these are icy. Right? These are the things that are way beyond what we call the snow line. So they retain their ices. And so whenever they come, whizzing by any star, even our sun, they should look like, comets. They should have gas and dust coming off, but a more was wrong. And so we, basically turn this into an actual paper. You'll see there's the two students, me and Aaron. It was a really tough class. And John was the instructor. No one had done these calculations, and so we ended up actually publishing this. You'll see it on the second author, not the first. Even though me and Aaron did roughly the same amount of work, to determine who got the first author, we did rock, paper, scissors. I lost. I'd like for my experience to this day. Biggest shame. And you can even see, right? We lay out this exact same thing that I talked about, right? And there's two ways you get a bunch of garbage into the galaxy. One is rocky, but doesn't seem to quite give you enough. The other is icy and gives you plenty, but then you saw all this rock. So circling all the way back to the thing we discovered a week ago. So it turns out we actually might be starting to see the differences between those two ideas. So if you take the moon was rocky, but the other two were not. So this is an actual image of the new interstellar object called 3I Atlas. 3I because it's the third interstellar object, and Atlas is the most discovered by the survey. So this is an actual image of 3I Atlas, and you see it's fuzzy. Right? You can actually see some fuzziness to it. And you can actually quantify that. Right? So stars, they're infinitesimally small, but when you take a picture of them, right, they look like circles because they're passing through the atmosphere. You can say, does this interstellar object look like a star? And the answer is no, right? The stars are more compact than the interstellar object. So there's some gas and dust that's coming off of this object. So it must be like a comet, unlike a moon world. So now that we've found a total of 3 of these, you can actually start to see those differences. We just got unlucky with the first one. Because a moon was rocky, had a weird shape. It looked like it came from an asteroid belt. Whereas these two other ones were round. If you look at their light curve, they look like they're just spheres, they're balls. There's no change in their brightness. They must be just ice balls, much like hydrogen objects. And so we're actually seeing these two different ways just produce a bunch of just garbage into the Milky Way. And so, right, we only have 3, so things are still a little iffy statistically, but we actually expect to find these, more and more over the next 20 years. And there's actually a bunch of work going on to see, got a bunch of, all the survey data we've already collected, and you go back with a better idea of what to look for and see if you can find any errors. Right? So the hard part is some of these are moving so fast that the computer's lighting algorithms just didn't pick up between different images, right? Because it's mostly been focused on what we know, which is the things in the solar system, which we know the velocity, we know the speeds pretty well, we know the orbits pretty well. So we're actually going back with a much more fine-tuned tone, saying we actually find any more of these that we just missed when they first came to the solar system. That's pretty much it for now. At least hopefully I've convinced you that this era of time-domain astronomy is really exciting, and even things where we either had predicted but never actually confirmed, or things that we didn't even expect to find for the last 5 or 6 years. We started to really not find one, but not find 5, 6, a dozen. And now we can start to do some really interesting things. So we've really opened up a new window to the time-domain universe, which is really exciting. So thanks. Yeah.
You hypothesize the shape, contours of a we don't really know that.
I mean, the brightness changes by a factor of 10. So you would have to have square root of 10, at least a factor of 2.5. And you start to account for things like composition. It's got to be at least 3, and from the people who study asteroids, what the composition is. So it's probably 5 to 7.
But it could be some.
It could be, oh yeah, I mean, it could be anything where your one axis is, 5 or 6 so long.
Are you going with Star Trek 4? Is that what you're going with, Chuck?
Well, no, I've got some things where there are people, and I don't mean the ancient aliens. If phone is going to chase it down to see what it looks like.
So that's an interesting point, because that one was unfortunate, because actually, so the solid points are going to be the solid.
Yeah.
And you can see, so the Earth's orbit is in blue. We actually discovered this one on the way out.
Yeah.
And so there was a window of like 4 days where we could have actually launched something and gotten it going fast on the catch. And then, yeah, like 4 days, and we barely knew that this was even interstellar within 4 days. But so that's actually an interesting point, because this is the new one, 3i, and it'll be behind the sun at its closest approach, but it's going to pass right by Mars. And so the reason we put this paper out a week ago was to claim that it's in we found it at school. But it was also to try and kickstart the Mars, because there's a whole bunch of things, orbiting Mars, and say, can you take all your spacecraft, which have been looking down at Mars, and point them up? And we have never tried. They have said, we've never tried, but we are willing to try for some of them. They're not going to do it for like the things that got there within the last few years. But for a lot of the older satellites, they're willing to actually see if they can point them in the opposite direction to take a picture. Because right, as these things get closer to the sun, the heating increases, you can really see how much ice is on the surface. But since it's going to be behind the sun, you can't do it from here. But with the Mars things, there's actually a good chance we can use really good images if it works. It's always hard because you're talking to spacecraft that's light on its way, But that is a good point. There's
It could be wrong.
We had talked about Vera Rubin before the presentation began, and I mentioned there's like the estimation of like 6 million solar system objects that it will find in its 10-year mission. I haven't seen anywhere prediction of how many interstellar.
So this is where, the low numbers have been killer, because it's hard to do statistics, but it's at least a dozen.
Mm-hmm.
And that's where,
Have you tried taking like that paper that you did for class, the estimation?
Yep.
And
so basically, the question becomes how unlucky. So, the moon was rocky, and the idea is basically we just got unlucky with the first one. Right? It means if I told all of you to flip a coin 10 times, there's at least 2 people that would get 10 straight heads and 10 straight tails. And so, getting one of these, right, the question becomes how unlucky were you? Because if most of these are like the Moon, we'll find probably a dozen. If most of these are like the other 2, then we'll find 100. The question becomes, but that's where we can do interesting things, right? Because that's, the real question is how often do you produce these types of things? So we can actually start to quantify that, which is really interesting. But the Vera Rubin will be very good for us. One of the 2 things that will be very good.
It looks very close.
Yeah. Mm-hmm. That's so there's definitely some really interesting, because I mean, this is where we know planets around. There's pretty much at least one planet, not multiple, around every star. So if every star goes through this, planet, messy planet forming process, how efficient are you at keeping all of your stuff? Right? If 20% of your stuff gets thrown out into the galaxy versus 10%, that actually has some pretty big ramifications for how many planets you have, right? How often life can happen, right? And how they are. So we can actually start to measure those numbers instead of like we did in our paper, just guess. Right? So there's some interesting things there. Yeah.
Neat project, thank you, neat presentation. About how many man hours are currently monitoring this project?
So I know CanStars employs usually 2 to 3 postdocs. So usually, so I'm a postdoc, but I'm also one of the fellows, so I get to pick what I work on, which is nice. But A lot of the surveys, especially the big ones like Pansars, are paying 2 or 3 people, a year. So basically their job is to look for these types of things. And then for the smaller surveys, like a Sensor and Atlas, usually you have no dedicated people. But that's where, especially with like Vera Rubin, which at least until a few months ago had money for paying people. That's where they at least plan to have like 5 people doing this pretty much all. Right? Because coming back to this question, if you can identify an interstellar thing early enough, you can muster, some sort of mission to try and go to it, right? Like that is the ultimate goal, right? Is to actually get something to go to one of these and spook something or take an actual measurement. Because the downside to the light curve is that you're just seeing reflections, right? And so while we have an idea of what most asteroids are made of, you don't know until you know, right? We can make a good guess, but you really want to know, is it exactly like the asteroids in our solar system, or is it 10%? Is it 50%? And so to do that kind of stuff, you want to go with it. And that's why hopefully Vera Rubin will have the money to pay us.
Any other questions for Dr. Bucker? Let's thank you all more.